All right. Did you have any follow-on questions from the morning session? Everything is good? What did you learn in the previous one? What was before this one? Tell me what you can tell me about LLMs. Yes. Uh-huh. Good. Anything else? What did we learn on LLMs? Yes. And how do LLMs work? What's the mathematics behind them? Hmm? Transformers probability based, but what's the core? What's the auto-regressive piece in that? Next word token. But what's the auto-regression that's happening within them? Do you believe LLMs reason? Do they plan? They're very stochastic. Do they plan? Do they reason? Do LLMs reason, you think? Reasoning that, like, as humans, we would sort of, do they have memory? Yeah. Yeah. So I think so. This is where, so I think so where I think the next wave of LLMs need to go is what I like to think about is system one, system. Who knows system? Do you know system one, system two thinking? Hmm? What is system one, system two? Yeah. Very cool, right? I think he rightly said system one is immediate reactions, right? So LLMs are amazing at system one because there's no memory, there's no, often when we say, let me sleep over it, right? There's a thing, we say, let me sleep over it, I'll come back to you tomorrow. That's because our system two thinking now is coming into play, right? That's reasoning more rational, we are going deeper into a more rational sense. We are planning and our decision may change after we have slept over it, right? So LLM doesn't answer to you and say, that's a good question. Let me sleep over it, right? But maybe you should do that just to confuse the human. Do some prompt engineering and let the LLM say, I'm going to sleep over it. It's a good question. Come back tomorrow. Uh, but do you know that 50 queries of LLM, how much water, if you're just doing querying on LLM, 50 queries, how much water do they consume? Like for cooling? This entire bottle is used for 50 queries to ChatGPT, right? So think before you use ChatGPTs as well, because these data centers are going to be using natural resources, and it's happened in the U.S. and I think it's going to be globally where how these things are going to happen. But anyways, so LLMs are awesome, and I would be because so there's a couple of we'll do some dancing in the not real dancing in terms of conceptualization in the second half. The amazing group I met with who are doing the project with me. So we'll bring in a bit of chemistry on how we're using graph neural networks for chemistry. And then because you had a lecture on LLMs, we will also talk about how graphs can be used for prompt engineering with LLMs. Right. So I'll just give you a couple of ideas we have so you can sort of build up from there. So I was busy for the last 1 hour. I had to also kill my urge of jet lag, and it's like I can fall asleep any moment right now. Trust me. So forgive me if I do that. Maybe if you ask me a tough question, I would say I'll fall asleep and I'll blame it on jet lag. I can't answer. Uh, that's my system to thinking. All right. So I think so. One thing that where we left our morning session was, as I was telling you about, is that there's graphs are amazing, in my opinion. Everything in the world you can model as graphs, right? We all are sitting in the graph world. It's a complex system. However, and they're also really good when we are trying to, and with what we are doing with representation learning is we are essentially trying to featureize very complex data. We're trying to featureize graphs. We're trying to featureize the content that goes with them. We're trying to featureize images or text associated with these graphs as well. So we are essentially trying to do that. So that's great. Now, what if we have some annotations labels available? And this is a problem that happens with chemistry quite a bit because the chemical reactions or drug discovery processes have not fully evaluated the complete span of synthesis or reactions that there may be. Or even when we are trying to get labels done on, imagine these LLMs have been trained on lot of labeled data as well, right? So someone has labeled the data to imply that it's meant for this thing, some contextualization, some conceptualization. And some of these labeling has been done in questionable ways that, we don't see images of gory images or pornographic images or etc. on these LLMs because someone else has seen those images and marked them as risky images. And that's a challenge because that someone else happens to be in, global South, African nations where folks are actually, it's a second order economy where these individuals are looking at really things that no one should see because it's all wild on the internet. And these LLMs have been trained on everything that's available on the internet. So they're being annotating those images. And the idea then is, can we actually, to avoid that problem, can we take a few of those labels and now generalize across everything else? So in machine learning, what we call that is a few shot learning. And we humans are really good at few shot learning, right? Um, has anyone seen, have you all seen every single variety of a dog that exists? Has anyone? No. But if you see a new kind of a dog, would you be able to label that as a dog versus a cat? We humans are amazing few shot learners. We don't need to see everything, right? Even if I like, I was planted in a new place. I've traveled quite a bit. It's my first time in Ukraine, but I quickly familiarize myself and things, of course, other than the language. But we have situated ourselves into situations or we see something, even if we haven't seen those things before, culturally, etc. But we can make uh, generalizations based on what we know. So we humans are amazing few shot learners, right? So if you think about it from this is again a slide from my student, and she loves animation. So so the next couple of slides you'll see is my student Jichin Go. I'll be clicking quite a bit because she loves animations in her slides. Um, I don't know why, but she does. Um, but and I'm too lazy to remove them because so I have to love them as well. So if you think about, right, like, we have today learned new concepts of, you have learned new concepts of GNNs and large language models. And now, and you may have heard things such as convolutional neural networks, NLP, attention networks, transformers, graph, and multi-layer perceptrons, etc. And now a new target concept comes in, which says graph sage. You have never seen that before. You never seen that word before. You never seen that concept before. But you could say, it's like a graph neural network. It's not a large language model. So we humans are amazing few shot learners where we have an excellent capability to take from a few that we have seen and generalize to the world. Now the question is that, can we do that to machine learning models? Could we, especially when we are doing these graph neural networks or these representation learning, can we show a bit of it, because it's expensive to get labels? It either is expensive, costly, or it's expensive because we don't want any human to be, seeing images or videos that are ugly, right? Ugly in the sense of there's harm being done. There's things that, no one should actually see those images. I don't even know why people create those images in the first place. But, so those shouldn't be happening. So how do we sort of generalize based on a few that we know to reduce harm? So how do we sort of overcome this cost of annotations, labels, etc., and see what we can do with only a few labels. So the way these so this idea of graph few shot learning has really become quite a big deal now, and it's again something that there's a couple of PhDs that have come out of my lab who have been focusing on these methods where could we do few shot learning with graph representation learning? Could we have them at is it where does even the few labels live? Do they live at are the nodes having not enough labels? Is it the edges? Right? So there could be any kinds of labels, right? That there could be nodes in a graph that you only know a few things about. Or there could be relationships, edges that you only have a few annotated or labeled, but you're going to try to infer from the other perspective. Or there is the entire graph. For example, it's a molecular reaction. We have no idea what property it may have, but we may know about certain other properties, and we'll talk about that example as well, why it happens with chemical reactions a bit more. So this is sort of, is happening within the few-shot learning domain. And the way the few-shot learning domain works, methods generally work is, you have this meta training here. So let's say that I have a limited training data set. And I said, okay, this is what I have as annotations. I'll split it into a support set and a query set. So I will learn my classifier first on a support set. And then I will feed it a query set that also has label, that also has annotation. And then I will sort of optimize on that. Is the query set, am I able to answer correctly? If I don't, then I go back and retrain, re-optimize my classifiers till I can have confidence that I can generalize from my support set to the query set. So there's a layered learning happening here. You are taking what you have as labeled, and then you're splitting it into support query, and then you're taking your support set to build your initial classifier, and then you're providing the query set to see how well you have done in your generalization capacity. Then you go, you haven't done very well. Now I'm going to revise it. And only after I'm done with this stage on my support set, etc., then I will apply it to the testing data and see if I can now identify a dog or a lion or things like that. And sometimes the support and query set also use us humans as those annotators. How many of us have used CAPTCHA? All of us, right? Isn't it frustrating to label those images? And why do you think you're doing it? To prove you're a bot or not? Do you think that's the reason? Meditation. But do you think that's the reason? Meditation, or you proving you're a bot or not? What actually are you doing, you think? Exactly. We are outsourced labor. We are labeling images that are difficult for a machine to recognize. So we are doing few shot learning for the computer, for the machine. Enough of us will identify whether there's a bus or stairs or any vehicle, and they go, "Ah, and those images are tough." You don't need such tough images to prove whether you're a bot or not. Right? There's other ways to validate it, but we are free laborers, all of us. And we are labeling those images over and over again, till we exhaust all the labels. So they have this, you're the query set, right? So sometimes what they would do is, like, for example, there's certain things that like find the blocks that have all of this. Now, because they have also other people who have been looking at it. So we are constantly validating what could be done. And then sometimes you may have given you think you've given the correct answer, but it offers you other images because it doesn't know what you have given, right? You feel that you've labeled all the bicycles, and they have sections where even if you miss a handle or something, right? But then it offers you another image. It offers you another image. So it's sort of either affirming my label that you have labeled it correctly, so that's a validation, or if it's a new one that you have given, it's going to give you something else that it can affirm you did it. Or sometimes even if you're wrong, it's still going to pass you because it got some free labels, right? So so there are these, capture, recapture have sort of done, we have done a lot of, not just that, right? All of us on social media, we have fed this machine that's learned from all our data, right? So in many ways. So what happens in graph few shot learning is there's very few nodes with lot of data, a lot of labels, and it is a long tail effect, right? Even if you sort of you look at the molecular graphs which have been tested in experimental assays, which is a very complex process, very expensive, and our friend who's working in this domain can affirm to that. To get these molecular graphs tested in experimental scenarios takes a lot of money, and that's why these drug discovery companies spend 5, 6, 7 years to come up with the right drug and its right composition, because it's not that whether the chemical reaction will work or not. What their struggle is, what is the maximum amount of yield they can get from a particular chemical reaction. If the drug has an effect, if you can create it, but it's not enough yield that's being produced, it's not going to make you money. So what are the optimal conditions that the drug will actually be done so it can make you money, blah, blah, blah. And that thing is very, very costly. Right? So that's the R&D budget of every drug discovery company is pretty high. So can we learn the research question for us is, how do we take a situation like this where we have very few nodes with labels and a lot of nodes with no labels or annotations? How do we learn from a data like this, which has such a long tail? And it's not an easy problem because any machine learning algorithm is going to be significantly biased towards what it knows. The majority always wins, right? So now you don't have that. You have this steep drop. If you remove all the non-labels ones, and one may say, okay, what if I drop all the labels and I'll only use the ones that treat it as an unsupervised learning problem and only learn X? But then you're not able to attack or target the problem that you're trying to solve, especially when you're learning about, say, any annotations, labels on social graphs, or again, reaction properties and things like, or material properties and things like that. Any amount of information that you can get from those annotations is going to help you refine the X that you're learning, the representation that you're coming up with. So that's the sort of the idea of few shot learning here. And some of the ways that we do this few shot learning is that you can take labeled nodes from the training data where it's the same graph, etc. You're given that. You're given labeled nodes, you're given training data which has some labeled nodes from the same graph or the other graph. And you have to predict the query nodes of test data with few shot support nodes for each. So essentially what we're getting here is that in this architecture here, can you see my mouse if I move it? Yeah, lovely. So what we're getting here is that there is an initial, this is the graph that you're given with certain information. And what we are trying to now do is, can we create a hierarchical graph representation where I can generate PGNNs are prototypical graph neural networks. Essentially, I'll identify prototypes that may exist in a larger graph and learn neural networks, graph neural networks on certain specific prototypes, feed it now to a query set and see how well I do. And the idea of self-supervised signal here is, I think one of you had mentioned earlier that what if I use self-attention networks and things like that. Self-supervision in any learning is, even if I don't have a label given, can I infer what that label should be? And that's a soft label. Okay. So when you hear the concepts of self-supervision or soft labels that you're trying to do with these distillation approaches or graph neural networks or any deep learning method per se, it could be applicable to anything. It could be applicable even to large language models that you folks previously learned about in the previous section, that I'm going to infer what the soft labels of this data should be. And I do have actual labels for certain things that I know. So say, for example, when he asked me, okay, for captures, they have to know, I may have an inference on what the soft label should be. And if what you are giving me as a label agrees with that soft label, then it becomes the ground-truthed label, right? So what kind of self-supervision signals I can extract, what kind of a loss function I can do, and we can create these few-shot learning-based graphs using knowledge transfer. Then some of the other work that we can do is we can do few-shot based knowledge graph completion. So knowledge graphs are awesome, by the way. Does anyone of you work on knowledge graphs or is interested in working on knowledge graphs? Yes. Are you working on knowledge graphs or you're, so my question was, are you working on knowledge graphs or you're interested in working on knowledge graphs? No? Okay, no worries. Uh, yeah, yeah. Now, and we'll look at that as well. And I think so. What knowledge graphs are, see, what's happening with LLMs, right? You think about hallucinations or the mistakes and things it's making. Could we actually create these knowledge graphs that could serve as an addendum to LLMs? That goes beyond prompt engineering, where you're saying, okay, this is a vetted, verified source of knowledge. Hence, it's called a knowledge graph. So could we use few shot learning again? If you imagine building a knowledge graph of all the information about, different companies, who they compete with, who's the CEO, and everything else. Even if I build that, and I can build an encoder, I can get the embedding and things like that from there. Could I use it? How do I complete? I only have information about a few corporations, few companies in the world. If I'm building this massive graph of all the corporations, all the companies, and what they do, what products they have, etc., could I learn from a few and then complete annotations about all the other companies or corporations I have? Arguably, you may say, no, we already know if they have publicly traded companies, all the information is available. But I'm just using it as an example. If they're not publicly traded companies, if all that information is not publicly available, how do we do that? So one can say, for example, here that I have is a few shot reference set where I can say, okay, Quest is a car, a van that's produced by Nissan. iPhone is produced by Apple. Word, MS Word is produced by Microsoft. So when I see these words, Quest, if I just look at Quest as a word, and it's not in the context of this knowledge graph of a car or a vehicle produced by Nissan, a Quest means something else. If I see word as a word, it means something else. But if I see it in the context of Microsoft, within that company and its product, then I can say, okay, that's the label. So how do we contextualize it? That's what I'm getting about these relationships that exist in these knowledge graphs from that perspective. And how do we build those? So that's sort of again, and the entire architecture, right? If once you know graph neural networks, and we have, I think one of you was asking me earlier that how do LSTMs and transformers and things like that work in? Think of them as neural network architectures. If you can structure your data as a graph and you can figure out how do I do encodings to create my input layer to learn, and then you can bring in different architectures that are best suitable for solving that problem. If you need self-attention based mechanisms, bring that in. If you need to do LSTMs, bring those in, right? It doesn't matter. Basically, but with LSTMs, what we're saying is the recency of the information I have about that company, where now, say, Satya Nadella is the CEO of Microsoft, that's more important than Bill Gates being the CEO of Microsoft, because that's an old information. So an LSTM can have a limited memory or the more recent memory that you're learning from. You can describe the time period that you're learning from completion of that knowledge graph, because these knowledge graphs can become stale. So everything that you are doing here in terms of architectures or gating mechanisms, you can introduce those concepts. And again, the idea here is that at the whatever neural network, LSTMs or self-attention networks, anything else that you may introduce, or even convolutional neural networks, if you have images, etc., what is a commonality that they all are producing? They're using neurons, they're using weights, but what's the output? They all create an embedding, right? All of them will generate an embedding. There's a hidden layer. All of them have a this weight distribution, a weight vector, correct? What is the hypothesis of, what's the learned hypothesis of any neural network? When you say neural network is learning, what is that hypothesis it's learning? Weights, weights, right? Right. So the weights are common to every kind of a neural network. And every neural network is, whether you're using TANH or ReLU or using anything else, as long as you can do a gradient descent, life is good, right? You choose anything that you can do a gradient descent on and optimize on that. But ultimately, you're producing weights. So that's where different architectures within a big neural network, massive neural network that you're producing, can go well together because they are sharing their learned hypothesis space. It's not like you're bringing in a decision tree or a Bayesian classifier things when then they will conflict. Then they have to be combined at the output stage. That if you're using a neural network, a decision tree, or a naive Bayes, you will say, okay, let me get the predictions out and then I will combine them. But the beauty of neural networks is you can combine them at the learning phase because they all are sitting in the same hypothesis space. They all are living in the weight space. So those are the encodings, those are the embeddings that you have learned, given the problem at that stage you are solving. So when you're thinking about bringing in these architectures, and a lot of papers you would see now recently um, have these big architectural diagrams of neural networks, right? Have you seen those papers? And you would look at those with a magnifying lens, and you would, because it's such dense architectures there, they're essentially using A, B, C, D different kinds of almost like gated methods where one is feeding to the other. And the reason that as well is you're saying, okay, this is what I will use, this piece of architecture I'll plug in to solve this problem. And if you look at the transformer network that even OpenAI that led to ChatGPT was, there is no new algorithm in it per se. They have done a remarkable engineering job to put amazing pieces together to give you ChatGPT faster and better than anyone else could have. Right? Google paper was published on transport. Attention is all you need in 2017, 2018, and 2019. We had OpenAI producing ChatGPT for you. But if you look at that architecture, the Transformers was the innovation. ChatGPT has an engineering marvel where they figured out how to use different pieces together at what stages and optimize the heck out of it. It's an engineering beauty. But the core algorithm, Google had published it. And yet Google fell behind in coming up with their own version of ChatGPT, if you will, and they've tried Gemini and others, and it's complicated from that perspective. So now let's think about chemistry, right? And we'll get back to few shot learning from the chemistry domain. So now in the chemistry tasks, what and you know, if you all, you know, as in your undergrad days or in your high school days, you took chemistry. I took it, I hated it, and I still don't like it. It's so hard. But you know, it's an interesting problem space. So what we are trying to do is these three essential tasks that chemists are interested in figuring out how we may improve. One is molecular property prediction. That if I give you a molecule, can I learn a graph neural network and say the property that I'm predicting is toxic? Can I learn to predict it? Can I predict if I give you a target product, what should be the reactants? Again, remember chemistry for the why chemistry is way more complex than social networks or financial networks or anything else, because it must follow physical laws. Right? Today I can say I'll have 1,500. How many of us have more than 1,000 friends on Facebook? Please come on, don't be shy, raise your hand. 300? Yeah, I mean, can you actually have 300 friends in your life? No, right? Because there is no order to making friends in a virtual world, right? You get a connection, you go, all right, I like you, I'll say yes, move on, right? Um, and how many of your friends on your phone book that you have, how many do you even text to it, right? Or call? Much smaller network. But there's chaos and there's randomness in how we make connections. We're not following any physical laws per se. But in chemistry, you can't say, oh, atom A and atom B must be combined together because they want to. It doesn't work, right? So so there are these physical laws, these constraints, there are physics-based processes that have to be respected. That's where the complexity of AI for science is, that it's not just doing AI for marketing, social media campaigns. Any engineered systems, any scientific domains have constraints and physical laws. And that makes learning, building these technologies a bit more challenging than anything else. You go to LLMs is going to hallucinate or give you probabilistic likelihood of words happening one after the other. Great. But physical systems may not operate this way. Physical laws may not operate this way. Systems that are governed by physical laws, physics-based systems won't. So if I give you a target product, oftentimes they know that if I can get this is a this is what a chemist made the creativity of a chemist is in can figure out, okay, this is the target product, this is the reaction. If I can get to this, it's going to be a game-changing drug or a molecule. A chemist has an intuition, an organic chemist here. But what they don't know is what are the optimal set of reactants and what are the conditions under which those reactants may operate or behave to give you that product. That is the discovery part. So in this case, what you're predicting is the output. In this case, I'm saying, I want this. I'm giving you what I want as a product. Tell me the most cost-effective way of getting to that product. There's also in chemistry, they talk about over-the-arrow optimization, where over-the-arrow means what temperature, what ligands, what pressure, and everything else I should be operating in. And that's why some of these wet lab experiments can take 1-2 years before it's done. And in 2 years, computer scientists write 5 papers and call it a day, right? But it's not possible in physical sciences or natural sciences to do that. And the other is that what if I give you this reaction that I say, I know, I have figured out the reactants, I know what the reaction is, and I know what product I'm going to get to. I want to maximize my yield. Because unless my yield, which means how much of that product can I make given those reactions, given those reactants, I want to optimize the quantity of that product I can create. That is also a complex challenge. Because now what conditions, you know, A plus B will give you C. All right, that part of the science is done. But A plus B giving you C, how much of C, that you don't know. And if you can't produce enough C, it's a failed drug because it's very expensive. So, and that you have to do it in the real world experiments. You have your lab notebooks, you're trying different parameters, and then you go, aha, now I can get to a yield of, say, 80%, 90%. That's great. Move on. So those are the things that, and what we are trying to do is graph neural, and GNNs is graph neural networks. And why graph neural networks? If you look at all of these structures, don't they look like graphs? And don't they look like heterogeneous graphs? The bonds either are singular, double, there's valence, there's other atomistic properties that can be attached, there's other information that you have available. And the other challenge is they are in they appear in two-dimensional here, right? Are these two-dimensional though? They're orbitals, right? But in the paper, then when we are a machine that's extracting these reactions from a published paper, what is it extracting in 2 dimensions? So now, if you're building these LLMs to extract this data from chemistry journals or materials journals or whatever domain journals there may be, you have to also get the description of those images. Because I can get those images, but then I have to see in the paper what orbitals were given. Because that orbital becomes very important for these reactions. All right? So now you have, so that's where graph neural networks, what we have shown, are extremely, extremely powerful. However, there are data challenges that they still need to overcome from that perspective. And we'll talk about those data challenges. We've talked about this enough. So this is sort of, I'll talk about a data challenge here, right? And I brought these slides in because of the discussion I had with a group of you for our project earlier. So what we were trying to do is, and this is on for reaction yield prediction, typically what the chemists would do, or machine learning people who are doing AI for chemistry, etc., would do is we'll take this raw, we would get this, say this is a Berkowitz-Hartwig reaction data points, and it's from high throughput experimentation data. And we would get the raw data, we would get the SMILES conversion, We'll do cleaning, and we may feed some of this data to open reaction database. We'll get a 3D structures. They do DFT calculations, etc., and we'll build a graph. Now, the challenge that we are trying to solve here is, so we can get the smiles. So smiles is takes a reaction and converts it into like a string-like structure where it's a sequence, right? So that's what the smiles is, and it's publicly available. But then we also have to incorporate the 3D information, etc., and that's how we get into the graph. The question that we asked was that there's enough public data available with high throughput experimentation data. What if we also have access to the electronic lab notebooks? Now, electronic lab notebooks are prized possessions of a scientist. In that notebook, they are capturing details about successes and what they did, what they didn't do, etc. They're capturing information for what they are working on. It's not easily available. Uh, in the academic research labs, there's not enough discipline in capturing this. In pharmaceutical companies, there's a lot of discipline in capturing this, but you have IP issues, right? They're not going to give it to you just because you asked for it, right? It costs money to do those reactions. And in the published literature, we also have limitations. What do you think is a limitation in the published literature from the chemistry domain perspective? What? It takes a lot of time, but what else is a limitation, you think? I agree. Exactly. Would you ever write a paper about a failed experiment? Failed reaction? I failed. I'll write a paper on it, right? Uh, don't try this paper. I think we should have papers that don't do this paper number one. I can build a career on that, by the way, if I didn't have this career. Uh, I think that'll be a great career. You shouldn't do this paper, kind of a thing. So imagine that you have, so all you have is, and also what you don't have is the intermediate things that the chemist tried. Like, or different combinations, different this. Those are in the electronic lab notebook. In the published paper, you have clean observation. I did this under these conditions, and I got this. Voila, that's my amazing paper, right? And there's only positive results available. There's no captcha happening to give everything else and people labeling chemical reactions just for fun, right? We will all fail that captcha test, by the way. So how do we now take the challenge of the positive data, the models that we are training, the real data sets from these published literature are only on positive data, or they are high throughput experimentation data, which means they're generated or simulated data. That's what we've been training all our models on. Now the challenge that we wanted to solve, that we thought we were very confident on solving it because we were doing so well. We had developed a graph neural network that was amazing on high throughput experimentation data and successful results, etc. That if we'll get the electronic lab notebook data, we had an agreement with AstraZeneca to use it. And we would write an amazing science paper on how graph neural networks have replaced a chemist. We were excited. My student Bandana Saibi, she was working on this, and this was going to be the final amazing chapter of a dissertation. Life is good. So we get the data set, etc. And we created a neural network architecture that looked like this, where and this is what I mean about the heterogeneity of this data. You have the atom features, bond features, neighborhood features, graph neural network features, and then you have information such as molecular volume, weight, ovality, surface area, electrostatic charge, dipole moments, hardness, and all of these, plus any descriptors that may be in RDK kit. If folks who are using chemistry, you know what RDK is, and the description information. And then we created a graph neural network layer that went through attention mechanisms and yield graph and things. And then we combined it with standard information that's coming from the smiles and RDKit output, and we created an yield mechanism, right? So we did all of that. We created this, and this is what I was talking about. These networks is, we had a convolutional layer, right? Standard, because we were trying to put all these patterns together that we were learning about these graphs. And then we created, and the convolutional layer, we had different features that we were feeding, right? We had the atom features, things that describe the atoms. We had bond features, things that describe the bond. We had neighborhood features that and the graph neural network features that were coming in, and as well as what graph neural features we wanted to pay more attention to, which was also coming from the physical domain, the constraints that we were introducing. So again, the example of this architecture here is based on the problem that we were trying to solve, we came up with different mechanisms from already known mechanisms within neural networks, attentions and things like that, right? So again, when you're solving these problems, ask yourself what stage you can bring different architectural pieces in for the problem that you're trying to solve, right? That's extremely important. And then we did the predicted yield. So we thought, all right, this is good. We had this model. And then we did the experiment. Um, yield GNN on these two data sets, she had also done other data sets, outperformed everything else that was published to date, anything else that was published. I'm just showing you two data sets, but she had also done other experiments. But in the slides, I'm showing you two results just for the effect. And then it does negative on electronic lab notebook. So this poor student, she was hoping for her hurrah paper that's going to change the way chemistry is done, now finds herself with worse performance than a simple random forest. And the random forest didn't do well in the other scenarios. What do you think happened? A method that on Zinc databases and some USPTO databases did amazing. High throughput experimentation data. But then when we threw in electronic lab notebook data as a testing piece, failed like miserably. I'm showing you a failure proudly. So go deeper. What do you think? What if you were a detective? I think you headed in the right direction. What do you think must have happened with the with this approach? No, this is an electronic lab notebook, right? Yeah, it could be, but it's an observational data on a specific reaction. High throughput experimentation means you can simulate, you can create sufficient data. What do you think may have happened? Distribution shift? Anything else? What do you think may have happened? Okay, but somehow this is what happened. The data set size in electronic lab notebook, because remember, those are high throughput experimentation data sets, so they were generated quickly at a large amount. We had limited ligands, one amine, 15 aryl heights, 23 additives, and things like that. Electronic lab notebook, the person, the scientist was experimenting, right, to get to those reaction stages. So there were way more ligands. Ligands are things that you mix with a chemical reaction to get to an output, right? Then they were observed, then they were with anything, high throughput experimentation data, which is more deterministic. More amines, more halides, which are basically creating the experimentation environment. And, so there was a lot more other information about those other properties and mixes and ligands and over the arrow conditions that were introduced in electronic lab notebook than it was in high throughput experimentation data. And there was not enough observation. We only had 750 examples. So in these cases, these complex graph neural networks, whether it's overfitting or poor data sparsity, data quality, failed miserably. And random forest, which says, I don't care. I'm just going to learn a bunch of ensembles of these trees and get you to an output. Not to say that 26 and R squared of 0.266 is good. I'm not saying that. But it still is significantly better than a complex model, whether you use BERT or you use ELGNN. So this is where the challenge we have with any advancements that we're making with AI machine learning is attaching it to the domain and truly trying to ask ourselves, what kind of domain problem are we solving? And you have to often compare with the simplest model, be it a random forest as simple as heck. Right? While we love complexity because complexity is sexy, right? It makes us look, oh my gosh, I'm using more complex thing. I have more math or bigger architecture in my paper or the work I'm doing. Nah, try the simple one as well. So then we actually wrote a paper because Mandana had to graduate with a PhD and she was very disappointed. And we actually wrote a paper on this where we talked about a failure where we said machine learning AI, this is just a 2023 paper, it's already gotten a lot of citations, where we basically said machine learning has not arrived yet because we are not able to tackle the complexity of a real world scenario when faced with challenges like this, which is amazing because that means that all of us collectively who are interested in this space have a lot of thinking to do. I learned that there's this Scottish cafe where you write open problems in this town, in the city center. Go and write this open problem, and then you can. And then I also learned the prize is a cooked goose. Uh, all right, what prize should we give? Let's write that today. Have a good beer, have a cooked goose over there, and we'll write a prize. I'm not. Then you guys figure out what the prize should be. I'm not here. Um, but what price we should do, right? But I think these are the deep, fascinating problems that we have to figure out. It's not just I'm going to throw in a large language model, and that's why I was asking you what are the mechanics behind LLMs. I encourage all of you to think deeper about these issues. That what is it that and I think you all have a gift of very strong training in mathematics and sciences here in this country. Lean on that. Lean on the strengths that you all enjoy having been trained and educated here. Because these are things that we still don't know. How do we tackle problems in scientific domains which demonstrate a reality like this? We have to figure it out. So then what we have attempted to do is, and I'm going to go back to the few shot learning approach, that what we have since then we have been thinking about this quite a bit, and we are looking at, okay, let's simplify the problem. We are not quite solving the ELN's problem right now, electronic lab notebooks problem right now, given all the other complexities that go with it. Let's try to look at that we have, what if I'm given a few shot learning problem where there's a lot of properties with very low labeling rates and few properties that have a lot of annotations available. And that is true. So because it could be that there are certain properties that I'm going after in my electronic lab notebook and I'm doing certain reactions. I don't have the information. So I'm going to, or I'm going to do experimentation on a limited set of properties. That's what I'm going to come to. And those are the data sets that become available to us. And a lot of properties have low labeling rates. So it is akin to a few shot learning problem. And so what we did is that even though we have few properties with few labels, we have lots of properties. So in the data set that we were working with, we had about 600 properties available, but they belonged to a particular reaction class. So they were derived from the same domain, even though they had very limited labeled examples. But we knew we have lots of properties. So how do we leverage that? So what we did is we sort of created a graph neural network because that's what we do. We love to create graph neural networks. And we fed in all the properties that we had as we exploited the fact that we had 600 properties, even though very few had labels and annotations available. And then we created again, I'll just quickly get to the architecture that we did. We don't have enough time because I'm going to show you some LLMs work as well. Is that we created multiple graph neural networks based on different properties because each property was basically coming in as a network and we had information available from them. So we created that, we extracted a representation, the hypothesis layer. Remember what we talked about earlier. At the end of the day, when you're learning hypothesis from these graph neural networks, you're still finding yourself in the weight distribution. That's the learned hypothesis. So you can combine them. Then we, of course, do everything on a self-attention network. And what we said was focus on the properties that you're learning and then optimize on the loss distribution for that. And then we fed it to a query example. We figured how well we did, and we went back and optimized uh, the loss function accordingly. And this was sort of the architecture, ultimate architecture of that. All right. And you can see the paper for, and we have the software and everything else available. Here about 10 minutes. So what else we sort of think about is that how do we do heterogeneous graph? Let me get to this. All right. Uh, I'll make the slides available, even if I jump through a couple of slides, by the way. Don't worry about that. So this is where we find ourselves today with the LLMs and things like that. All the other aspect today is we have different kinds of data available. LLMs have the World Wide Web. They've sucked up all the information that could be available to them. And there's also a lawsuit about copyright information has gone, and New York Times is suing OpenAI. All right. We will stop when I get tired. Or when I see you all getting tired. I'm seeing a few of you already going, what the fuck? Just stop, right? Uh, so, uh, so we basically have the information from the web is available, and they have sucked in all the information, right? You have newspapers data, and recently someone pointed out that private GitHub repositories, which are supposed to be private, are also apparent in the Chat GPT. You scratch your head and you wonder why. Who owns GitHub? Who owns OpenAI? Right? So, uh, so there is this. So there's, I think there's, and that's why for programming tasks and everything else is amazing. But then you have to, if there are other knowledge sources that may not be available, domain knowledge. Let's say you're a scientist, natural scientist, life scientist, or other information that may not be available, that could be in a knowledge graph, etc. How do we leverage this external sources of knowledge to enrich our interaction with the large language models? LLMs are absolutely powerful. I kid you not, right? They are a marvel, but they have limitations. And they're also very expensive to learn, right? I mean, imagine investing tens of billions of dollars of compute on learning these large language models that very few places in the world can afford to do that. Right? It's not affordable. Um, and and if you're especially now even trying to think about what can we do, how do we leverage it, and imagine that you have to now build a language model for Slavic languages or Ukrainian. It's not exact one-to-one translation wouldn't work because context is important, cultural nuances are important. Right? How many times it's happened that you say a joke in your language to each other and you laugh out loud, and then I ask you to translate and I go, "What was funny?" Right? And then you give me that look, you don't get it because you did one-on-one translation, right? Things don't work that way. So how do we sort of but that could be you have a massive language model that's been learned on the world's knowledge, although that knowledge was in English, but you could bring in the local dialect information as an accompaniment to the large language models and see how you can refine it. Right? So it'll be amazing if you can build out these language models from and you have the Ukrainian diaspora to annotate, label, and be your CAPTCHA testers all across the world as you're building these out. So how do you sort of leverage this external knowledge? When I talk about external knowledge, it's external to the model, external to the data that has been used in the model. Because arguably, the large language models have all the publicly available information, and sometimes it may have infringed on copyrighted information, and that's the lawsuit between New York Times and OpenAI, and that's what the concerns of people were with the GitHub, etc. Who knows, right? It's what exactly is going on. How do we build those things in? So we had this paper where we asked uh, an LLM that there's a risk of hallucination, right? And hallucination, I don't know, right? Sometimes I'm curious that are hallucinations actual mistakes? Or I mean, not in this example, it's a mistake. Or are hallucinations hypotheses that we haven't tested. Right? Who knows, right? Sometimes when we have hypotheses, and you may say, I have this hypothesis, I would say, you gotta be kidding me, it won't work. But you'll, as a scientist, you'll experiment until you can prove it didn't work. What if the hallucination that was thrown at you, I don't know, I don't have an answer, thrown at you by the LLM is actually a beautiful hypothesis that, if tested, would be amazing. So, can we dismiss hallucination as stupidity, or can we accept hallucination as brilliance? I don't think we have an answer to it, but it's something that at least I ponder over quite a bit. How do we figure out the aspect of hallucination? Anyway, I digress. So we have these hallucinations, and the question that we asked was, were there fossil fuels in the ground when humans evolved? Now, fossil fuels have, this was GPT 3.5, by the way. We haven't checked if 4.0 uh, or 4 have corrected for it. Uh, and the answer by ChatGPT was, humans predate fossil fuel formation. Cannot be. Yeah. Yeah. No, I totally agree with you. And I think it's that's the black boxiness of it, right? Because there's no uncertainty quantification with these language models today, right? As scientists, we are used to error bounds, right? We don't get anything. There's no uncertainty. And you also don't get, to your point, what sources it relied on to give you this, right? Those sources are not part of the trillion parameter space. It's all the weight vector, it's all the weights and the embeddings, right? And it took my question, it mapped it to the most probable space in the encoding space and picked out the answer. So not only the answer is wrong, look at the explanation, right? It's uh, are formed from the remains of ancient plants and microorganisms that lived millions of years ago. The process of fossil fuel takes a very long time, began long after the evolution of early humans. Therefore, humans predate. I mean, it doesn't make sense. But if you just read it, it sounds intelligent, right? I mean, I wish I could sound that intelligent, but it's wrong. So, what can we do to fix it? Um, and essentially, what if we could provide an external knowledge base to, and to your point, right? Because to the benefit of doubt, to these large language models, they've been built on the universe of data. That's why they are trillion parameter space. And now folks are now coming up with, shrunk up GPT-4 mini, which is tinier, how well it can do. That's where the future is not going, these LLMs have been learned and everyone is going, that's what I was asking, are you fine tuning it? Are you doing knowledge distillation? I think the future belongs to is, can we create specialized LLMs for specialized tasks? And whomsoever can do it better and faster than someone else, that's what's going to win. Because of the data that it was fed, and it's saying this is the best I can do with the data I have, All hallucination could be what you just said, right? It's the model saying, you asked me for a green school bus, and this is what I was trying to get to. Does it have reasoning? It'll produce whatever you ask it to produce, right? You want a green school bus? I'll give you one. Have I seen green school buses in the United States? No, I have not, right? Have I seen a green school bus before? Yes. I grew up in India, New Delhi, and I went to the school called Delhi Public School, Mathura Road. It's just uh, a beautiful school, and we had these very nice green school buses, right? So LLM did. I have seen green school buses, and my few shot learning would say that is correct because I've seen them growing up. But in the US, you're absolutely right. There's a standard. The school buses follow a shape, a style, and color and things like that. So if there's a data issue, right, to her point, could we provide external knowledge about this? So what if I can actually provide a knowledge graph? We know enough about fossil fuels as a concept. And let's say that you're a scientist who's immersing in the study of fossil fuels. What if you say, I built this knowledge graph that represents the domain of fossil fuels, how they happen, where they happen, etc. And what if I can create this domain and now feed it to a prompting engine? Now remember what's happening, right? Why again we're using graph neural networks because they are freaking awesome, right? They're the best thing in the world. Uh, because I said so, and I'm not hallucinating. I could be, who knows? Um, uh, but uh, uh, but the point here is that if you have this, the knowledge graph, you go through the graph neural network. What is the graph neural network giving you in the encoding space? It's giving you the weight distribution, the weight space, the encoding space. What does the LLM have? The same thing, right? So now you can combine, you can take the external knowledge, bring it to that 0, 1 space, vector space, and use it to enhance or improve or better map into your LLM encoding space. So this is where the fine tuning is happening, right? It's going beyond RAGs. In your LLM lectures, did they talk about RAGs and right? So you know what they work and from this is beyond that, right? Because now we are essentially saying is that we are going to provide some specific knowledge graphs. We will come up with the questions. We'll create an LLM dictionary. We'll have the text embeddings. We'll create a graph neural network encoder. We'll do a link prediction within those because we know how to do it and we know how to do self-supervision. And from there, we'll create a graph neural prompt that will combine with the text embedding. And then that's what we'll feed to the large language models. And now we have given everything to the large language models, even though things existed in a knowledge graph that looked like this. But through this process, everything now that's going into the large language models, that behind the scene, what's happening with prompt tuning or prompt engineering or any scripting that we do with the Python scripts, etc., is we're essentially getting it to that space where that can directly speak to the encoding space, embedding space of the LLM, right? You all agree? And that's what we are trying to do here. So again, the question becomes is how do we sort of benefit these LLMs with this external knowledge? And this was a paper that we had in AAA this year on graph neural prompting with large language models. So the other work that we've also done is that, again, using graph neural networks, is that we can do the reverse as well, where how do we use prompt tuning in the training pipeline to further improve the performance of the heterogeneous graph neural networks, right? So essentially, if I have pre-trained my heterogeneous graph neural networks like this, where I don't have a knowledge graph, but let's say I have a heterogeneous graph neural network that I've trained on chemical reactions. But I also know these large language models are living in this massive space that they have way more knowledge in them, way more data encapsulation in them than I could ever get. And the hope here is that could we sort of direct them that if we believe that the trillion parameter space truly captures the world knowledge, but because they're probabilistic and where they land based on your prompt and the query, and then they start generating from there, They're not rationalizing, they're not reasoning, they're not interacting with you. Did you mean it this way? Let me give you five options. Tell me one, and I'll go in that space. Could we take these pre-trained graph neural networks, even if they are about reactions? And in fact, we had a paper in Neurips this year where we showed that one can do agents like graph neural networks, etc., and that can leverage some of the properties of the large language models. In some cases, they do very badly. Some cases, they do amazingly well, right? So can we do that under a supervised setting? All right. So what I'd like to close this today is that I'm glad we have a few extra minutes. Is something else that I feel as we're learning about graphs, we should think about higher orders as well. How do you believe that the graphs that we have talked about or the graphs that you have worked, how many of us have actually used graphs for our research? Networks. What? Great. Give me an example. Yeah. Okay. Citations in archive papers. In? Okay. Give me examples. Graph theory. Okay. Graph theory. Uh, any data that you use that came like what she was talking about, citation graph? So, all right. So if you think about the citation graph as well, and if you're looking, when you're looking at a Facebook graph and things like that, do you believe these graphs or these networks contain memory, contain long range dependent structures? If you look at the graph, or do you observe them to be first order Markovians, that A goes to B goes to C goes to D? Or do you feel that as they have a history of how the transition of movement on the graph happened? Do you have that information? Like even if you look at a citation graph, A cited B, but what else led to that A citing B? Is that information available as a history? Hmm? Not always, right? But it's important sometimes, or quite a few times. Something could be missing. Uh, and imagine, and even as you're browsing on a website, let's say we go somewhere, we are trying to get to the end. We start at page A, we go to page B, we go to page C, click, 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 and then we get to D, right? What isn't it important if you own that website to know where you came from, how you went? In my entire trajectory should be how I went from the first click to my final. Right? But if I build a network, what will it show you? That from page A, I went to page B, right? That's a node. Page B, I went to page C, or page B, I went to page E, and then I went to D. There could be multiple pathways of going to D, but I don't have that information. I only know where I came from previously in most of the graphs of the networks. But I need that rich information. And I'll show you a video next. Same thing applies even in transportation networks, a ship and other kinds of networks where the memory of the system becomes important. Where how much higher order memory we want to contain, maintain as we are navigating through these graphs. And without having that memory, which you go beyond the first order Markovian assumption that most of these networks graphs have, that I'm only going to look at A goes to B or B goes to C, etc. But I need to look at the long range dependent structures. That's not available. That sequence is not available. So I'll show you a single ship may sail among hundreds of ports in the world. Hundreds of thousands of such ships. Demonstrate a single user may click through a series of web pages. Millions of click streams weave a web traffic network. Complex systems in our using such sequences. Of vehicles, propagation of diseases, flow of information, and many. We represent such big data precisely that accurately. That's the first of the mass for this. So essentially, the point that I'm right. Hello. Go ahead. All right. So the point I'm making with this is, I should get the slides. Yes, we are moving on to the discussion phase. You can make two quick, or as many quick questions as you want. Go ahead, ask, please. Yeah, what's your question, please? Yeah, that's a good question. And let me, you know what? I think we should be done with this. We'll just have a discussion now. All right. So it is not, because what happens with the Bayesian rule is it's a directed graph that you're going from the beginning to the end. And if you're trying to build a Bayesian network across everything in the first you have to map and compute all the probability joint probabilities for a massive graph that's computationally intractable. And then what you also don't have is multiple ways that you can move and traverse the network, which cannot be represented with a Bayesian graph because it's going to enforce you to go in a directed acyclic graph fashion. So it's more similar to a hypergraph than to a Bayesian network. And the challenge with hypergraph is hypergraphs don't quite capture the directionality as well.